Welcome to the UC5 showcasing video. In this video, we will show how the rigorous framework deals with a economic denial of sustainability attack in a 6GPPDR environment. We will present two integrated scenarios. Scenario 1 presents user plane DDoS attack, while Scenario 2 describes a control plane DDoS attack. The following rigorous enablers were used: Security Orchestrator SO from UMU, AI-driven decision engine AID from EBOS trust evaluation and enabler service functionalities from LNVO, AI-powered EDOS mitigator from OLU holistic security and privacy framework from ONE, and the rigorous Kafka was used to enable asynchronous and multi-domain communication. In total, 3 testbeds were used: ONE, OLU, and EBOS. The objective of Scenario 1 is to prevent economic denial of sustainability attacks caused by stealthy application layer DDoS against cloud-native 5G network slices. This scenario is focused on the cloud infrastructure. The system starts in a normal status. All the monitoring systems are in normal status, and no anomalies have been identified. Then, let us simulate the attack of a rogue UE against the user plane and see how the system reacts. We launched 2 processes simulating the low-rate app layer DOS attack, with each holding 1,000 multiple connections against the video stream component EDOS is monitoring all the scaling requests, and the first request was received from the horizontal pod autoscaling, a mechanism part of the Kubernetes cluster. The request is processed internally by EDOS and deemed as not malicious, therefore allowed. As the number of connections keeps increasing, the system detects it as an anomaly, as we will see next. A new scaling request arrives for the same component. Considering historical system usage data, EDOS classifies this new request as malicious, and the request is rejected. From the component available replicas, we can see 2 are currently desired, yet only 1 is available, confirming the rejection for the component upscaling. Now that we detected the attack, we will see how the rigorous framework reacts and mitigates it. EDOS sends the anomaly report to the ED via the rigorous Kafka broker. The AID determines the action to mitigate this issue and communicates it to the SO, which communicates with the OLU's custom K8s sidecar manager to trigger the UPF's TCP dump sidecar. This is done to determine the source IP of the device as originating the malicious autoscaling request. The malicious network traffic is identified and, similarly to the first scenario, an anomaly report is sent to the AID using the unified data format agreed in the project. Several anomalies are identified and reported to the rigorous SOAR mechanism. Here we can see some examples of the anomaly messages received from the AID. AID processes the anomaly message, determines the mitigation action, and sends it to the SO. The SO receives the MSPL policy from the AID and ensures its correct enforcement, in this case, by the PE agent, the policy enforcer mechanism available on the OULU tested. The PE agent receives the policy from the SO and reflects it by adding the respective drop rule into the 5GCU PFS IP tables, which we can verify the correct addition by observing the UPFIP tables. Later, it is possible to observe that the malicious UES can no longer connect to the video stream component as expected, considering that their IPs have been blocked. Moving on to Scenario 2, here the focus is to prevent DOS attacks against the 5G/B5G control plane network functions caused by malicious UES. Similar to Scenario 1, the system starts in normal operating conditions. TESF is used to assign trust scores to devices attempting to connect to the 5G/B5G infrastructure. We are using Open5G as the 5GC open source implementation and select one of the UEs to launch the attack, which corresponds to the UE forgotten by a PPDR agent in the course of a PPDR occurrence and stolen by an offender. The attack simulates the consecutive authentication attempts next to the 5GC authentication management function, AMF, by the rogue device. The device is able to authenticate next to the 5G infrastructure, as the AUSF logs present, but continues to send authenticate requests. The continuous authentication requests from the malicious device cause an increased load at the AMF. Considering these requests, TESF reduces the trust score of the UE originating such requests. The rigorous framework continues to monitor the events at the 5GC. When the trust score falls below the threshold, the UE in question is deemed as malicious. Following the standard approach, TESF informs the rigorous SOAR via AID, reporting the anomaly in question. AID receives the anomaly and determines the appropriate mitigation measure. The AID sends the mitigation policy to the SO. In the meantime, the malicious UE continues to perform authentication requests. The policy is received by the SO and sent to the PE agent. The PE agent enforces the policy by deregistering the UE and releasing the SMF context. This action is verified on the MonGODB manager to ensure proper enforcement. As last step, we verify the device is no longer subscribed at the Open5GS. Thank you for listening.